Hello folks, and welcome to this lesson on the organic nomenclature of cyclic compounds. By the end of this lesson, you should be able to name and draw cyclic organic compounds with varying side chains. So, up until now, you've been dealing with hydrocarbons that were all chains with branches on them. Why can't you take chain and connect the ends together and make circle? You can! You can make rings, and there are a lot of compounds that actually do use rings, even though we're not going to be seeing a lot of them in this particular course. Now, you basically take your chain, you close a chain, and that's how you get a ring. This being said, you're not really going to see a lot of rings that are under 6 carbons, and that's because of ring strain. Because, once again, let's look at the VSEPR around it. If you have a 3-carbon chain, each of these carbons is also going to have other things attached to it. So that means you still have 4 electron domains around each of these carbons. But if we have a triangle, you can't really have that angle be any more than 60 degrees, which is way lower than that VSEPR angle of 109.5 degrees that you would get in a tetrahedral shape. So because of that, there's a lot of strain on these bonds. They're all repelling each other. All those electrons are repelling each other. And so you're really not going to see rings that are 3-carbon or 4-carbon, because if you have 4 carbons, that angle is going to be 90 degrees, also smaller than 109.5. And even with a pentagon, that's going to be 108 degrees for each one, still smaller. Rings of 6 carbons are that first sort of shape that actually don't have any ring strain. And this is generally going to be what it looks like. So you can see that I have this 6-carbon ring. It's not a perfect hexagon though. What actually happens is that some of these carbons go up, some of these carbons go down, and then you get that 6-membered ring, and all of the VSEPR stuff works out. All of those angles end up working out. And so this is what your 6-membered ring is going to look like. Now, hilariously enough, my first organic chemistry course dealt a lot with these rings and also another stereochemistry type thing. And so they actually allowed us to bring in these structures to our exams to help us visualize what all of these things were going to look like. Now, one last thing that I wanted to point out is that these structures are not as spinnable as your chains are going to be. You can see that even with this structure, there's a little bit of wiggling that can happen, but you can see that in general, things aren't really changing where they are. And so this is actually going to have some effects on the naming and also the types of bonds and reactions that it'll be able to do, to undergo. But that's for another lesson. Now, with naming cyclic compounds, it's fairly simple in terms of the name itself. All you're basically doing is you have your parent chain name and you're going to stick on a cyclo right before it. The tricky part for this stuff is going to be the numbering. So here we go, we have our hydrocarbon. At this point, if you have a cyclic thing in here, it is going to be the parent chain. But where's 1? Which one's carbon 1? Because you have no distinct end. Well, you choose a carbon 1. Any one of them is going to be a carbon 1, but make sure you're following all of the rules that you followed before. So, we don't have any particularly important functional groups that would be part of the parent name, so we're going to go with our side chains, and we're going to determine our numbering based on the side chains. So if that's the case, we want the lowest number combination for our side chains. So that means one of these are going to have to be carbon 1. So if we say it's carbon 1 here, then you're going to end up with 1, and then that's going to be 2. So it'll be 1, 2, 2, which, not that bad. If we go the other way, what's going to happen is that if this is carbon 1, then you'll get 1, 1, 2. Which is a smaller number combination, and so that's how these carbons are going to be numbered in this compound. You cannot go the other way around because of the fact that it is not going to give you the smallest number combination, and therefore it is going to be incorrect. So if we're going to put this name together, we have chloro groups and methyl groups. So chloro is going to go first since alphabetical. So we have 1 chloro, and then we have our 2 methyl groups. So that's going to be 1,2-dimethyl. And now we have something cyclic. We're going to toss in our cyclo, and this is a pentane. And so here you go. This is the name of this particular organic compound. So here is a compound. Pause the video and try to name it. So here we go. The basics of it are fairly simple. We have 2 fluoro groups. It's cyclic, and there are 8 carbons in it. We also have a double bond, so that's also a cycloalkene. The tricky part, again, is going to be that numbering. So where is carbon 1? Well, you could say, well, carbon 1 could be there because then you get 2,2 for the fluoro, but you're forgetting about the fact that we have an important functional group here. This is part of that parent chain name, and so this gets numbering priority. You could say, well, I could put carbon 1 here, because then it would be 1, and you have your double bond, and then you go 2,2. That is a smaller number combination. Well, yes, technically it's a smaller number combination, but that's not how the numbering works. If this is carbon 1, your carbon 2 is here. You're following that parent chain, and you're following that functional group. So this becomes 1, 2, 3, 4, 5, 6, 7, 8. So this actually becomes a 1 with an 8-8 combination. Not great. So our last choice is this. Here's our carbon 1. We follow along to carbon 2, 3, and so on and so forth. Now you get that carbon 1 for your double bond, and then you get 3, 3 for your side chain group. Much better than the 1, 8, 8 that you would have gotten. So let's put this name together. Start with our side chain. So our 3,3-difluoro, it is cyclo. And then we have an octagon, so it's oct-ene. Now this is going to feel really weird, but remember that this is cyclic. This is all we have in terms of our functional groups. We only have literally this one. So that means because it's cyclic, this double bond is always going to have carbon 1 no matter what. If you have 1 double bond, it can't be anything more than carbon 1. So because of that, it is redundant to say that this is oct-1-ene because there's literally no other choice for that double bond. And so this is 3,3-difluoro cyclooctene. Now a few last things for you to be careful of when you are drawing these cyclic hydrocarbons. Make sure you're watching your numbers. Carbons can only form 4 bonds, and they will form those 4 bonds. And so you want to make sure you're not putting too many things or too few things when you are adding in things like rings and double bonds and triple bonds and things like that. Also, there is some naming stuff related to that whole stiffness in the rings bit, but that's going to be a different lesson. That's all for today. I'll see you next time.